Take a sorted deck of cards and cut it. When the bottom half is placed on top of the stack, the sequence of numbers breaks. If you try to find a specific card now, the standard binary search logic fails because the middle card no longer tells you which direction the sequence is heading. In LeetCode number 33, we deal with this exact data structure, a rotated sorted array. Even though the numbers jump at a pivot point, our performance target is still O of log n. To reach that speed, we must still find a way to discard half the data with every comparison. Because a rotated array is created by a single pivot point, any way you slice it in half will always leave at least one side untouched by that pivot. In this example, slicing at the 7 leaves the entire left side as a perfectly ascending, unbroken staircase. Our strategy is to identify which side is that clean staircase. Once we find it, we check if our target value is within those specific sorted bounds. If the target isn't there, we know for certain it must be in the messy half, allowing us to throw the entire staircase away. This logic keeps the O of log n complexity intact. We are still having our search space every time. We just use the sorted half of the array as a reliable anchor to decide where to move. We can manage this logic using a 4-block strategy. Block 1 is the standard shell. This is the basic binary search setup, initializing left and right pointers, and creating the while left is less than or equal to right loop. Block 2 is the lucky strike. Inside the loop, we calculate the middle index and immediately check if it contains our target. If it does, we return the index immediately. If we haven't found a match, we move to block 3, identify the sorted half. We need a way to tell which side of the middle index is the unbroken staircase without having to look at every number in between. We use the condition if nums left is less than or equal to nums mid. By comparing the leftmost number against the middle number, we prove that everything in between them must be in ascending order. Checking these two endpoints is an O of 1 operation that provides a definitive guarantee about the structural integrity of that half of the array. Now we enter block 4, the boundary check. We treat this sorted left half like a club with a strict door policy. To enter, a target value must be between the lower bound and the upper bound. We write this nested if, target greater than or equal to nums left, and target less than nums mid. We verify the target is greater than or equal to the floor, and strictly less than the ceiling. If the target is inside those bounds, we search the left by moving our right pointer to mid -1. If the target fails the check, we know it cannot be in the sorted section, so we move our left pointer to mid +1 to search the other half. Let's try an active recall. Pause the video and determine what the nested boundary check is if the right half is the sorted portion. The correct code for the right side is target greater than mid and target less than or equal to right. This follows the same logic. We establish the boundaries of the sorted section and check if the target is contained within them. Seeing the sorted half as a bounded box helps write comparisons based on spatial logic, rather than trying to memorize which way the symbols point. Let's trace a target of 0. Mid is 7. Since 4 is less than 7, the left half is the sorted staircase. Is 0 between 4 and 7? No. We discard the entire left half and move our left pointer to index 4. In the next step, our new middle calculation will land directly on 0, successfully finding the target in O of log n time. To retain this, don't try to memorize the code line by line. Focus on the 4 logical triggers that drive the search. Review the checklist. 1. The boilerplate shell. 2. The immediate check for the target. 3. Identifying which half is sorted. And 4. Checking the bounds of that sorted half. By identifying the sorted half first and then checking its specific boundaries, you can navigate a rotated array using the same binary logic as a standard sorted list.